what we're going to be looking at is multi-output circuits. And most of the designs that we're going to end up creating in actual industry are going to be more than a single Boolean expression. They're going to be a couple of expressions pulled together. So we usually have what is our combinational logic. And for us, this is our and or not gates of how we create an expression. And in here, from this expression, we can have multiple inputs. And we would have more than one output that is going to be created. So we're going to look a little bit about examples of these type of circuits. So the first thing we're going to start off with is we're going to go back to something we done in our very first lecture. And we're going to look at adders. You know, when I had some binary numbers I wanted to add together, we figured out, you know, what that process was going to be. Now, when we come to adders and we need to build a circuit, we're going to build it one bit at a time. And the way we're going to end up building these items is we have two types of circuits we can create. The types of circuits we have, we're going to call one a half adder, and then we're going to call the other type a full adder. And those would be the two different items that we have. What makes these different are what are the inputs. The input is the difference between these two items. For the half adder, it's just an A and a B. On the full adder, it's going to be an A, a B, and a carry coming in. So, you know, if we had numbers that we were going to add together, we could say, you know, this first digit right here, this is what we would call a half adder. It only adds two numbers compared to this one here in blue, because when we add that item in blue here, we need to add up a carry. Well, this would be a full adder, because we need to add three numbers together. So we can see that during the addition, we would need these multiple types of circuits. All right, so let's start with the half adder. And if we have our half adder, I need to generate input coming in of an A, input coming in as a B, and I'm going to produce two outputs. We're going to have S, and we'll call S, this is the sum, and then we'll have CO, and we'll say that this is our carry out. All right, so but the first thing we want to do is come up with our truth table for the circuit. Our truth table for the circuit is AB, and let's do it in the output in the order of CO and S. All right, so we have four possible inputs for A and B. What is 0 plus 0? Well, that's 0. What's 0 plus 1? It's 1. 1 plus 0 is 1 as well, and then 1 plus 1 would give us the value of 2, where 2 is a sum of 0, and we had a carry out coming out. Okay, so what we want to do is, from this truth table, we need to create our circuit. And in this creation, we're going to have two equations that are going to come out. We're going to have an equation for S, and we're going to have an equation for CO. Okay, to find CO, there's only one output that is going to give us the value. So we just need to look to see what inputs create that. And for that, that is AB. Okay, so CO is just A ended with B. Now for the S, we can put this into a K-map with these two values. And if you were to put it into a K-map, you would see that they're not adjacent to each other. There will not be any group you can group together. So we end up having two terms. One's going to be A bar B, which is this first item. And then the second one is going to be A B bar, which is the second piece. Now, in here, we can also say A bar B plus A B bar. We talked a little bit about this in a previous lecture where we said that is what makes up an XOR gate. So I can say it's A XOR with B. And that's that I can reduce it down to a single gate. All right, so if we have this, I can draw out my circuit. I have my XOR gate. That's going to produce S. What is that taking in? That's taking in A and B. And then I need to produce carry out. That's just an AND gate. So CO. And I'm just going to take A and include it. I'm going to take B and include it. When we have lines cross each other, if they have a circle in it, that's when we say there's a connection. So if we look at this, we can say this circuit right here is two outputs, two gates, two inputs. And that's a pretty compact adder, a half adder that we can create. Okay, so if that's a half adder, let's see what a full adder would kind of look like. A full adder is going to take in three inputs, an A, a B, and this will have a carry in. Let's call this CI. All right, so we're going to say this is our carry in. That's the CI. What is it going to produce on the output? It's going to produce an S, and it will produce CO, which is our carry out. Okay, so let's make our truth table. If I add all zeros, I get a 0. If I add 2 zeros and a 1, I get a 1. 2 zeros and a 1, I get a 1. If I add 2 ones, I'm going to get 2, so that's 1 0. A 1 and 2 zeros, that's a 1. 1 plus 1 is 2 again. 1 plus 1 is 2 again. And then 1 plus 1 plus 1 is 3. Okay, so now that we have the truth table, we want to take this truth table and create our circuit. In this setup, it's going to be useful for us to do a K-map. So I'm going to make two K-maps. I'm going to make one K-map for sum, and I'm going to make one K-map for carry out. Okay, so our sum will be, I'm going to do AB and carry in, AB and carry in. This is going to be the way I set up the K-map. And then we would read off our values on the truth table and fill them in. The outputs are going to be for S. We have nothing that is adjacent. For carry out, we will have a couple items that are adjacent. Okay, so in S, each term is on its own. So that's A bar, B bar, CI. Or next one is A bar, B, CI bar. Or I'm going to have an A, B, CI. Or I'm going to have an A B bar, and a CI. Okay, on carry out, I'm going to have a pair. I'm going to group that pair. That pair ends up being B, CI. I'm going to have another pair, which is AB. And then I'll have a third pair, which will be A, Ci. All right, so now we have this item as a circuit. I can ask again, could I make some type of reduction? Yes, it's going to be possible to make a reduction using XOR. The sum on a half adder was XOR. Well, we can kind of assume that there'll be a similar item for an XOR on our full adder. So let me write out this circuit again, and then we'll see how we do reductions. So I can make it into an XOR gate. Okay, so here's our sum, and I believe it will have an XOR because we saw it again in the half adder. So how am I going to do this? All right, what I'm going to look to try to do is pull out like terms. So I have a CI here. So let me pull out that CI, and I have an A bar, B bar. Let me make sure I got that correct. I think I wrote something down wrong. Hold on. Yeah, this one was supposed to have a bar. So let me clean some stuff up. All right, so we're looking at these two terms here. So that's A bar, B bar, or AB. And then I'll do the same with the CI bar. Okay, so I have CI bar, and then I'll have A bar, B, or A, B bar. Okay, so in this item, what we're gonna look to have is this term right here. That was my XOR. So let me change that to say it's CI bar with A XOR B. Well, on this side, this ends up being an XNOR gate. So that's a CI with A XOR with B with a bar over it. Okay, at this point in the term, I want to do some substitution. I want to take this to be X and an X bar. All right, so I want that. So I have CI X bar plus CI bar X. And what that ends up becoming is CI XOR with X. And then what I'm going to do is I'm going to sub back in my X. So I have CI XORed with what's my X? My X was A XORed B. So then that ends up being CI XORed with A XORed with B. So I can produce it in that fashion. All right, so let's draw out our circuit. And when we draw our circuit, I'm going to make a restriction. I'm going to say we only have 2 input gates. So I'm not going to be able to get this entire sum as one gate. I'm going to have it as 2 separate gates. All right, so the way I'm going to do it is I have an XOR gate that is taking in A and B. The output of that is another XOR gate that has to take in CI. And that produces my S. So I need to do 3 ANDs. So I'll put 3 AND gates out. The ANDs, if let's scroll back to the top, we see it's B, CI, AB, ACI. All right, so I'm going to have A and B for 1. I'm going to have A and CI for another one. And then I'll have B and CI for the third one. I need to OR stuff together. 2 inputs only, so I got to do the first two, and then I OR it with the output of the third AND gate, and that gives me CO. All right, so let's count up how many gates we have. So I have 2 XOR, I have 3 AND, 2 ORs. So in total, I have 7 gates. All right, so we have 7 gates. So we'll see, is there anything we can do with 7 gates to kind of make items a little bit better? An item that we're going to look to see is smaller number of gates can be a better circuit. It's really going to depend on how we get that final implementation on an IC circuit, whether or not this is true. But in the most general term, that is something that it's always the case. A smaller circuit will take up less space. A lot of times it'll end up being that it can run a little bit faster. All right, so with the sum, there really is nothing that we can make smaller. Sum was just 3 variables by themselves. Likely this is the smallest circuit we can create. You know, it could have been bigger. We could have left it at ANDs and ORs, but we kind of reduce it. So it's really the carry out. We have to ask ourselves, is there a way that we can reduce our carry out? Well, to reduce the carry out, we kind of need to think about it as being, can we share a gate from our sum? You see, let me scroll back a little bit. You see, in this circuit, the end result is I need a S and I need a CO. You know, that was that little box that we drew out. What's inside the box, the end user doesn't care about. They don't care if it's 5 gates, 7 gates, 12 gates. All they really need to know about is they're producing the correct S and they're producing the correct CO. So we need to look to see, could I share pieces? Sharing pieces means, is there something in our sum that could be used in our CO? Right now, there is nothing in common. You see that to produce S, you went through 2 XOR gates. To produce CO, you went through these 5 gates. If I could share items, I'm going to reduce the number of gates. Okay, so let's see how we can share. In order to share, I likely need to get into an XOR gate, because that's all that S is made out of. So let's see, can we convert any of this into an XOR gate? Well, the first thing I can kind of notice is I have a carry in. Let me pull that carry in out. And I have A or B. Okay, so what's an XOR gate? Let's just write this on the side. An XOR gate is A XOR B is A bar B or A B bar. So I got to try to get into that form. I have an A or a B. I got to get both variables in. So how can I get both variables in? We need to see, is there something that I can do to add in that both items have AB? Okay, in order to do that, I'm going to want to expand this item. And the way I'm going to want to expand it is, let's say I have A ended with a 1 or B ended with a 1. That ends up being A or B. So I got to look to see, how can I increase this 1? Well, to increase that 1, I need to have B in the term. I can say it's B or B bar. How do I get this 1 to be expanded? I need to expand it in terms of A. That's an A or an A bar. All right, so let's do that. Let's do that expansion. So I have A, B, or C, I. And now I'm going to have A with B or B bar, or with B with A or B bar. All right, so let me multiply through. So I have AB or A B bar plus AB plus A B bar. All right, so first thing we're going to notice is I have an AB and an AB. So I can just write that once. And then what remains is there's a theorem I can use called consensus. And with consensus, I will be able to remove out this AB. And when I remove that AB, I would get AB plus CI with AB bar. I think I wrote this term wrong. Hold on. That should be A bar. All right. So A bar B. And that gives us an XOR gate. So that's AB plus CI A XOR B. And now we have something that is shared. Okay, so let me redraw this circuit out now. I have an XOR gate going in with another XOR gate to produce S. That is A, that's B, and my CI. Okay, now to produce my CO, I need an AND gate that is taking in A and B. And that's this first term right here. This XOR, I already have that. That's this first one here. So I can use that output ANDed with a carry in. So let me put another AND gate. I'm going to take the green item. I'm going to take carry I. And then once I have those two, I can put them into an OR gate to produce CO. Now what am I using? I'm using 2 XOR gates, 2 AND gates, 1 OR gate. So in total, I have 5 gates. I have shed off 2 gates. This would be a better circuit because I have reduced the number of gates I needed by 2. Okay, so you can see that it's important that we can show that there's some sharing of terms. So next time, we're going to looking at solving multiple equations through K-maps and trying to do this item of sharing terms. So I'll see you in the next video.